All right, so far in chapter 1 of our subject matter, we've been talking about how to solve, a big thing was talking about how to solve algebraic equations. So we're actually, it's going to feel like kind of a big jump here because we're going from solving one equation to solving multiple equations at once, dealing with what we call a system of equations. So systems of equations. For now, we're going to stick with a world where we only have two equations at one time. And as a matter of how we're going to conduct things in the class, we're going to have the same number of unknowns or variables floating around in the equations that we're dealing with as we have actual equations themselves. So if we have two equations, sort of our default variables are usually x and y. So hopefully that seems familiar when we're talking about linear functions and so on. You should be used to seeing x and y together in equations at this point. So a solution is going to be, a set of x and y values. So now instead of just a single number, you're going to have a pair of values because you need both the x and the y that satisfy both of the equations in the system at once. So that's a bit of a difference. It actually turns out in terms of graphing things, remember, we're going to be dealing with linear equations. So I should have said that from the outset. But when you're dealing with linear equations, since we talked about these things have graphs that are lines, well, as it turns out, if you imagine sort of graphing a couple of these guys, the solution is basically the intersection point of the lines in question. So you really have kind of a handy visual tool for, have you found the solution? You can sort of plot the two lines and then see where they cross. We're going to focus on how to do this algebraically, on the other hand. And you'll notice if you look through the notes file again, keep in mind, I assume you've got the notes file handy while you're watching this, that we've got two main methods for how we solve a system of equations. We're going to take a look at each of them in turn. We'll start with the first method and then talk about the second one most likely in another video just due to time constraints. So the first method that we're going to talk about is what we call substitution. So we essentially, in that instance, we're sort of going to rearrange one of the equations we have to get a variable by itself and then use that in the other one. So let's take a look. It's probably easier to take a look at it in the context of an example than to have me sort of try to wave my hands and talk through it. So let's take a look at this first example that's listed here. So we have 4x minus y equals 3. Then we have 6x plus 9y equals 57. All right. So again, I'm sure we've all got better things to do. Theoretically, yes, you could keep playing around with pairs of values until you happen to cross a couple that work. But again, I'm going to take for granted we all have something better to do with our time than that. All right. So the idea of this substitution method is we want to get one of the variables in either of the equations. It doesn't matter whether it's the first or the second. Get that variable by itself. Now, looking at the two equations here, it seems like it'd probably be pretty easy to get y by itself here. I mean, we've sort of already been doing that, right? We spent all of section 1.3 looking at stuff and saying, let's get this in the slope-intercept form. That means we need to get y by itself. So yeah, we can do that here. If you rearrange this, there's a couple of different steps you could take. I would probably just subtract over the 4x, so you have 3 minus 4x. But then you've got to get rid of the negative, so you either multiply or divide by -1. So you'd have negative 3 minus 4x, or, let's see, 4x minus 3. So now, if we know an x value, we can find the corresponding y value. That's how the function stuff we've talked about works so far. But here's where the magic of this ends up happening. Now what we can do is take this expression for y, that's now in terms of x, feed it in here, and when we do that, we now only have one variable left in the equation, so it should be easier for us to come up with a solution. All right, so we'll have 6x plus 9 times this thing. We're feeding that in for y, so we have 4x minus 3 equals 57. Got to step over a bit so I'm not blocking what I just wrote. And then I'm going to go ahead and distribute the multiplication by 9 that I've got here. So we have 6x plus 36x minus 27 equals 57. We still haven't touched the right-hand side yet. Now, we can do a little algebraic song and dance from here, right? So we can combine these two x terms. We get 42x when we link those two guys together. We can also get the x stuff by itself by adding 27 over to the other side. So we said 6x plus 36x is 42x. 57, when we add over the 27, if I'm doing my arithmetic right, that gives me 84. And now from here, we just need to divide both sides by 42, and we've got x by itself. 84 divided by 42, and lo and behold, our x value that we need is 2. I'm not going to put a box around this yet because I'm not quite done. So I found the x value. Like I said at the start of the video, though, we need both x and y values. Now, the good news is it's not going to be too much work in this instance once we've got x to get y, because coming back to what we did to substitute in the first place, it's not too challenging for us to feed that x value in here and get the corresponding y. So 4 times 2 minus 3, and I hammer out the arithmetic on this bad boy here. 8 minus 3 gives me 5. So x equals 2, y equals 5. I'm generally okay with you writing the solution like that. You may, however, want to write the solution as like an ordered pair, x comma y. That's sort of like how you'd see it if you did it graphically, right? So the solution will be 2 comma 5 in that instance, and I'll put my box around that. Just on guard, like I said, because that's usually how WebAssign wants to see these things. It may say x equals y equals, but you should also be ready for it to want, like, parentheses, like an ordered pair on a graph. So that's one example down. So we've seen that substitution method in action. Works really well in scenarios where it's not going to be a great, headache to get one variable by itself. The next example on the notes file is actually, it's even easier to isolate y if you take a look at it. So let's do so. All right. So the system for our next example looks like this. 2x plus 5y equals 24, and we have negative 3x plus y equals 15. So the numbers may be a little bit bigger, and you may end up starting and looking at this and saying, well, I don't see how it's easy to get either of these variables, either x or y. Like, so we did y, you could have gotten x by itself also. But you may look at it as like, I'm going to have to do a bit of work to get either of those by itself looking at that top equation. That's the catch. We don't always have to use the top equation. So let me go ahead and clear this off so I can just go to town on this next example. But this time around, it's actually easier if we focus on the second equation. So to get y by itself here, all we've got to do is just add over the 3x. So, and if you'd written 15 plus 3x, that's totally fine. But now we can just take that guy and shove it right into that top equation where we see the y. So we have 2x plus 5 times 3x plus 15 equals 24. So now, same routine from before. We can distribute the multiplication by 5. So we have 2x. We multiply 3x by 5, we get 15x. 5 times 15. It's dangerous, I'm doing the arithmetic in my head here, but we should have 75, I think, when we work that out. Equals 24. Again, we still haven't touched the right-hand side yet. All right. So now, when we take a crack at this, we can combine the two x terms. So we have 17x, and to get rid of this 75, I need to subtract it from both sides. So 24 minus 75, if I'm working out the arithmetic right in my head, that's going to give me, what, negative 51, I think? So, again, don't hesitate to double check me on this, but I'm pretty sure I'm all right. So that means to get x by itself, I just divide by 17. So I have, that is not a negative 15. It should be a negative 51. Don't know what happened there. So negative 51 divided by 17. Pause if you need to work out the arithmetic. It's fine. But we should get an x value of -3 out of that guy. And just like we did in the previous example, now that we know our x value, we can stick it back into this guy to get the corresponding y value. So y equals 3 times -3 plus 15, and that would be -9. -9 plus 15 gives me 6. I said x equals -3, y equals 6. As an ordered pair, that would look like -3, 6. So that's our solution for this one. All right. So the substitution method, again, as I've said, works really well in scenarios where it's not, we don't have to put a ton of work into getting a variable by itself. It still works even if there is more algebra that goes into it. But it turns out in some of those situations you may find another approach to be more beneficial, and that's what we'll look at next time.